In this video, we're going to take a look at the first question on the 2009 AP Chemistry Free Response questions. And they say, use the information in the table below to answer part A. Which of the two acids is stronger, HOCl or HOBr? Justify your answers in terms of Ka. And so if we look at the Kas, Ka is an equilibrium constant that shows the extent of the dissociation. So stronger acids dissociate more, and so they should have a larger Ka. It's kind of a little tricky, but this 2.9 times 10 to the minus 8 is a larger number than 2.4 times 10 to the minus 9, because minus 8 is larger than minus 9. So when I answer this question, what I'm going to say is, for A part 1, HOCl is a stronger acid than HOBr due to HOCl having a larger Ka value, indicating that HOCl dissociates more than HOBr. Okay, draw the complete Lewis electron diagram for the acid you identified in part A. So that's HOCl. So what we'll do is we have 1 plus 6 plus 7, we should get 14 valence electrons. Oxygen will be our central element. If you're ever in doubt, just bond it the way that the formula looks. And so we'll give everything 8 electrons. Of course, we do not include hydrogen in that, because hydrogen's in row 1 on the periodic table. And when we count here, I got 2, 4, 6, 8, 10, 12, 14. So that looks like a good Lewis structure. Okay. Part B, write the equation that occurs between hypochlorous acid and water. So this is just a simple dissociation reaction, but with water. So normally we would have this break apart into H plus ClO minus 1, but because we're reacting it with water, we're going to see how this changes. We'll add water here, and instead of it being H plus, this will be H3O plus. Okay, so very similar. In C, it says a 1.2 molar sodium hypochlorite, which is bleach. That's what this is. If you've ever looked at the back of a bleach bottle just to see the ingredients, it's sodium hypochlorite. It's prepared by dissolving solid NaOCl in distilled water at 298 Kelvin. The hydrolysis reaction, this occurs, so we've got a different reaction. I'm going to copy and paste this. Write the equilibrium constant expression for the hydrolysis reaction that they just gave us. So this is C part 1. Okay. So this would be Kb, actually, because we produce hydroxide. So we get HOCl hydroxide to the first power divided by only OCl minus, because water is a liquid, so we won't include it in the equilibrium constant expression. Let's look at part 2, what they asked for. Calculate the value of the equilibrium constant for the hydrolysis reaction. So here's what's kind of interesting is this is a Ka reaction. This is a Kb reaction. And therefore the same acid-base pair. So what we can use is we can be really, really clever, because when I first read part 2, I was like, okay, what information do I have to use a rice table? And I'm not saying that rice tables aren't important. I'm just saying a way that we could use this is by using the Kw expression, Ka times Kb. We know that Kw is 1.0 times 10 to the minus 14. The Ka was given all the way up here as 2.9 times 10 to the minus 8. So we can get Kb. So we'll divide each side by 2.9 times 10 to the minus 8. And when we do that, we get 3.45 times 10 to the minus 7 as our Kb. Okay, part 3 here. Calculate the value of hydroxide in 1.2 molar sodium hypochlorite. Okay, so now we get a Rice table. So what we're going to do is we will paste our reaction. We're going to make a Rice table. And water, of course, will not be part of our Rice table. We'll do 1.2 molar, 0, 0, minus x plus x plus x, because we have to shift right to have some product in order to reach equilibrium. So we're going to get Kb, which we've already solved, to be 3.45 times 10 to the minus 7. And notice how part 1 feeds into part 2, which feeds into part 3. That's typically how these ones with parts for a specific letter will work. And we're going to end up with x times x over 1.2 minus x. We will use the 5% rule to get rid of minus x. That way we don't have to use a quadratic. And we're going to end up with x squared over 1.2 equals 3.45 times 10 to the minus 7. And x, when you solve that out, that will equal 6.43 times 10 to the minus 4. Now, we've got to make sure we answer the question. They asked for the value of hydroxide concentration, and I've just got to verify if that's what x is, and it looks like it is. So that is the answer for part 3 there. Okay, part D says a buffer solution is prepared by dissolving some solid sodium hypochlorite solution in a solution of HOCl, so common ion. That's what a buffer solution is. I can't spell, goodness. The pH of the buffer solution was 6.48, so calculate the hydronium concentration. That should be almost like suspiciously easy, because if pH equals 6.48, we know that the inverse of pH is 10 to the minus pH to get H plus, which is also the same thing as H3O plus 1. So 10 to the minus 6.48. That will give us 3.31 times 10 to the minus 7, which equals H plus or H3O plus 1. Okay, and that was D part 1. D part 2, let's see what that one asks. Indicate which of HOCl or Cl or OCl minus is present at higher concentration in the buffer solution. Support your answer with calculations. So the equation that I'm thinking of here is the Henderson-Hasselbalch equation, which is on the back of your periodic table, and it says pH equals the pKa plus log of A minus, which is your conjugate base, over your acid, HA. We're just going to plug in what I know. I know that the pH is 6.48. I know that pKa is minus log of Ka, and that the Ka we had already been given, 2.9 times 10 to the minus 8. So what I'm going to try to do is I'm going to solve for this fraction. And what I know is that if this fraction is greater than 1, this fraction, then OCl minus will be present at higher concentration. But if the fraction is less than 1, then that means my denominator, HA, is present at higher concentration. So when I do this, I am going to get the pKa, negative log of 2.9 times 10 to the minus 8. I get 7.54 plus log of A minus over HA. And you might already know the answer now that you know that the pKa is 7.54, because the pKa represents a halfway point of a titration. But we will subtract 7.54, and we're going to get negative 1.06 equals log of A minus over HA. And we'll take 10 to the minus 1.06, because the inverse of log is 10 to the power of whatever's on the other side. And that equals 0.0876, which equals OCl minus over HOCl. And so what I know is that HOCl must be greater than OCl minus. You might include a few words there. The only thing that gets a little tricky for me is they just said which one is higher in concentration. So I answered that, and then they just said to support my answer with a calculation. So I have a calculation to support my answer.